Hey everyone. We are going to talk today about electricity for the first time. And so in class, I had you guys start thinking about what you know about electricity. And depending on who you are and what you've done, you knew lots of different things. Today, my goal is going to be to set a little bit of groundwork so that we all kind of have the same ideas going forward. So, before we talk about what electricity is, we really need to talk about what an electron is. And so if we think back to middle school science, you probably remember that matter is made up of atoms. And atoms are the kind of smallest parts of matter that we can isolate. And you may have even looked at what is inside of an atom. And in the middle, we have a nucleus, which is made up of positive protons and neutral, not charged, neutrons. And then around the outside, we have negatively charged. So remember, these are positive. We have negatively charged electrons. And I'm going to be a little bit vague about where they are around the outside. When you get to chemistry, you're going to discuss. And just like we talked about with light and how there's lots of different models for light, and the more we learn about light, the more we refine that model. The same thing's going to happen with atoms because um, there's been a lot of different ways of thinking of atoms, from something as simple as, essentially a round dot to something that looks like this, to something that looks even more complex in terms of the electrons. So again, we've got the positively charged protons, the non-charged neutrons, and the negatively charged electrons. And we'll sometimes abbreviate electron as E minus. Now, what you might notice here as we look at this drawing is that these electrons are really, really, really far from that nucleus. And that is true. Like, if we looked at an atom, you will find that most of the space of an atom is empty space. And it's this empty space between where the nucleus is and where the electrons are. And so as a result, it's a lot easier for us to like come in and grab a electron than it ever would be for us to come in and grab like a proton. Because to get to a proton, we'd have to go through all these like layers of electrons. But to get an electron, we can just grab one from right out on the outside of the atom. And so when we talk about electricity, what we're really talking about is a flow of electrons. So these electrons that are part of any matter that we have, if we give them the right encouragement, can be able to move around. And we can take them off of atoms and move them around. And we're going to talk a little bit about how that happens. So to start to understand that, we need to start to think about conductors versus insulators. So a conductor is something that allows the flow of electricity. While an insulator is something that does not allow the flow of electricity. And if you think about like what wires are made of, right? Wires are there for electricity. And what are they made of? They're made of usually a metal. And so a metal is a really good example of a conductor. And if we think about what's on the outside of those wires so that the electricity doesn't flow into us and our skin, it's usually something plastic or rubbery, which are great insulators. So we're going to learn just a little bit of chemistry right now to help us understand why certain materials are really good conductors and certain materials are really good insulators. So if we zoom in on these atoms, there are a lot of different ways that atoms can bond together. And the two that these two materials use are really important in shaping how electricity flows or doesn't. So let's start with a conductor. A conductor usually has something that we call metallic bonding. And yes, obviously, this does usually happen with metals. And in metallic bonding, the atoms are next to each other. So we've got a couple nuclei going here. They're very close to each other. So close, in fact, that instead of electrons being around one of these, like this, or another one, like this, the electrons are essentially just shared. And so electrons don't really know where they belong and don't really feel like they belong to one particular atom. And that means the electrons are really free to move around. And if we think back to what is electricity, it is a flow of electrons. Okay, so if this kind of bonding allows for really easy movement of electrons, it seems like it'd be really good for electricity. For the record, we call this arrangement of electrons the sea of electrons. That is the formal scientific term. And it's the reason why metals make such great conductors. Now, over in the insulators, we have something that's called covalent bonding. And this is probably like the first kind of bonding you learn about. I would not be surprised if some of you had heard about it in middle school. In covalent bonding, what ends up happening is that two atoms each have some electrons that belong just to them, but they also have electrons that they're going to decide to share between them. And so each of these electrons is really tightly connected to one, or in some cases, it's really extra bound and it's connected to two atoms. That makes it really hard for us to get those electrons to move around. So in covalent bonding, we don't really have any free movement of electrons, and that's why they do not allow for the flow of electricity. So as you start to learn more and more about different materials, you'll start to be able to look at what kind of bonds are in those materials and to predict whether or not they're going to make good conductors or good insulators. All right. Now, when we talk about electricity, there are three major quantities that we're going to talk about over and over and over again. And I'm actually going to throw a fourth in here because we'll talk about it a little bit as well. Three quantities are voltage, which you might also hear called electric potential, current, which you might also hear called nothing. We just call it current. And then resistance. And to understand these three and what they have to do with electricity, I'm going to use one of my favorite analogies for electricity, and that is a stream like flowing down a hill. So if we think about like a mountain stream, we've got a lot of water, And what's going to happen? It's going to flow down the stream. So in this analogy, current would be how much water per second flows past a certain point. So how many molecules of water are going past this spot each second? Voltage would be how much energy the water has as it's coming down the hill. And in this case, it would be basically like the height of the hill. And resistance is how hard it is for the water to flow down the hill. So I would say that's something like the rockiness of the creek bed. So if it's a really smooth, easy stream bed, then the water is going to be able to flow very easily. But if it is like rocky, or like what if there's like major boulders or even a dam, like obviously that's going to make it harder for the current to flow. So the exact same is true when we're looking at a circuit. So in a circuit, the voltage is delivered to us by the battery or the wall outlet. And so what happens in a battery is a chemical reaction goes on that strips electrons off of a chemical and gives them a lot of energy, and then it pushes them out to do something. And so depending on how big your battery is, what voltage it's rated to, is it a 1.5 volt AA battery, or is it a 9 volt battery, or is it a 12 volt car battery? It'll have different amounts of energy as it leaves the battery. Just like if this was a less steep hill, we would have water with less energy, less desire to get down the hill. All right. Current is very similar. Instead of water per second, it's electrons per second. And specifically, it is not just electrons per second, it is the amount of charge that flows per each second past a certain point. And then resistance is how good of a conductor your circuit is made of. So are you using like nice copper wire that conducts really well, or are you using something that's like a tin alloy that maybe doesn't conduct very well? We are going to get back into resistors in a couple of days pretty intensely, or resistance, because it turns out that we sometimes intentionally add resistance to circuits for certain purposes. And so we're going to come back to that shortly. All right, let's think a little bit about what units we use to measure each of these. Voltage is measured in volts. By the way, both of these take their name from Alessandro Volta, a famous Italian physicist. Current is measured in amps, or the full name for an amp is amperes, which is a capital A. And resistance is measured in ohms, which you're going to love this one, is a Greek omega. So these are the units that we're going to use. And something that I think is really important to know about units in electricity is that they are really big. So when we think about the units we tend to use in mechanics, so motion and forces and all of the things we've studied so far, they're very human-sized units. A meter is, well, a person is just a little taller than a meter. A second, it's a very countable amount of time. A newton is a very detectable amount of force. And so we're used to these very human-sized units. That is not really the case when we get to electricity. And part of the reason, and in fact, most of the reason, is how we initially discovered electricity and defined it. And in fact, 1 amp, we basically initially defined it based on the amount of force you could feel from the current in a wire at a certain distance. And it turns out it takes a lot of current to make any noticeable force. And so as a result, 1 amp is a lot of current. You'll often see in this class that we're going to deal in milliamps, which is a much more common current to be moving through a circuit. I mentioned one other thing that I was going to bring up, one other quantity that we might use, and that's power. We've actually talked about power before. Power is how much energy is used by something each second. And for us, like if we think about a light bulb in a circuit, power is going to determine the brightness of the bulb. Or if we were thinking about like a heater in a circuit, it would determine how much heat is being given off. So we are going to talk about power, especially later on in this unit when we talk about light and how we generate light using electricity, because it turns out there are ways that use a lot of energy each second and ways that use a lot less energy each second. When we use these quantities in equations, what variable do we use? Well, volts is easy. It's actually a V. Resistance is pretty easy because at least it's an R. Power is a P. Current, for the record, is a capital I. So when we start looking at equations relating these to each other, keep that in mind, that these are the variables we're going to use. And in fact, that's going to be my next video. We're going to talk about something called Ohm's law, which brings voltage, current, resistance all together. Okay, have a great day. Thanks.